All right, so we are starting our notes on pH today. So in your notes page, we have just finished up Bronsted and Lowry and their definition of acids and bases. For our pH, we're kind of going back to that Arrhenius definition of acids and bases and considering hydrogen ions and hydroxides. So this first piece, we have our pH scale. In the middle, you can see that they've labeled pH. And so those numbers listed there in white are our pHs. And that is reminiscent and similar to the things that we talked about in lab. You can see that 7 right in the middle is our neutral pH. And that things that are less than 7, so 6, 5, all the way to 0, are the acids. And things that have pHs bigger than 7, 8 up to 14, are our bases. This also labels some other new things that we want to discuss. Molarity, we'll remember that from our solutions unit. Molarity means concentration, and so we're looking at molarity of hydrogen ions here at the top. That's what these numbers are. It's our concentration of our hydrogen ions. In our pH notes and in our formulas, when they want to talk about concentration of hydrogen ions, they will label them in brackets. That bracket means concentration. And then down at the bottom, we have our molarity of our hydroxide ions. And so again, concentration, they put it in a bracket. Okay. I want to note, guys, if we start out here at neutral, it has 10 times 10 to the negative 7th for its concentration of hydrogen ions. And as we get more and more acidic, going closer to our pH of 0, notice what happens to our hydrogen ion concentration, 10 to the negative 7th, to the negative 6th, negative 5th, negative 4th, all the way until we get to 1. I know that it kind of looks like that's a big number, but if we remember back to scientific notation, negative exponents are actually very, very small numbers. So as we get less and less negative and climb up to 1, what's happening is that things that are more acidic have more H plus in them. They have higher concentrations of H plus, and things that are acidic will have less OH minus. On our basic side, things that are basic, notice their concentration of the hydrogen ion. They have less H plus, and they have more OH minus, which is what we had talked about when we talked about the Arrhenius definition of acids and bases. So pH, what does this pH mean? It's a measure of the hydrogen ion concentration in solution. It's a measure of how many hydrogen ions there are in solution. And to measure that, we have a formula for it. pH is the negative log of your hydrogen ion concentration. Here's our purple formula chart. So you can see under the title of solutions and acids and bases, this formula is right here. You don't have to memorize it. We also have a second formula that has pH in it. This one is not solving for pH. It's solving for our hydrogen ion concentration if you're given pH. And again, that formula is also on our chart right there. So you don't have to memorize them. What's going to be important is that you know how to use them and which one's appropriate. So in problem 1, it says determine pH. We want to calculate pH. That's what we're trying to solve for. They gave us a concentration. They gave us molarity. And they told us that our substance is H2SO4. If they give you a specific substance, if they give you a formula, it's a good idea to think to yourself, is this an acid or a base? H2SO4 has that leading hydrogen. It's an acid. When you put something like H2SO4, which is a strong acid, into water, it breaks up into an H plus and then an HSO4 minus. It's a strong acid. It's one of those 6 strong that we told you guys to know, and so all of its molecules are going to do that. If I'm telling you that we have 0.00012 moles, or molar, H2SO4, Because it's an acid and it's strong and it puts out all of its hydrogen ion, that first one into solution, then this concentration they've given you is the concentration of hydrogen ions. If what they have given you is an acid, then the concentration that they've given you is the concentration of hydrogen ions. So I know my H plus, and I'm trying to solve for pH. That means I will need this first formula. pH is equal to negative log of our hydrogen ion concentration. And in this particular problem, it's 0.00012. Guys, this is a heavy calculator unit. You definitely need a calculator for your logs, but it's still important to show your work, to show us what you're putting in your calculator. So here, the negative button all the way down at the bottom by our enter, negative. Our log is over here by the 7. And when you type that in, it's going to bring up a parentheses. And we're going to type in our concentration of 0.00012 and hit enter. Guys, we don't really teach you the sig fig rules for logs, so it's just safe to do 1 to 2 decimals when you're doing your pH calculations. So we could say 3.9 or 3.92. Either is fine. We're not going to be particular on sig figs with pH and POH. So a pH of 3.9 makes sense because it's an acid. We're right. We're brilliant. The next one says, what is the concentration? So now we're trying to solve for concentration, and they've given us pH. So we're going to use this second formula in this one. So we're going to take 10 and raise it to the negative 6.1. Type that into your calculator, guys. 10 and negative 6.1. 7.9 times 10 to the negative 7th. Now, pH does not have a unit, but concentration does. So we would say molar. Solving for POH is super similar. If pH is the measure of hydrogen concentration, POH is a measure of hydroxide. And we have 2 formulas for that are super similar to the ones we already just used. POH. They're asking us for POH. They've given us a concentration, and they've told us our substance. Guys, this is a base. We see that OH in it. When it separates in water into its ions, it puts out OH minuses. This concentration, since it puts out OH minuses, is its concentration of OH minus. It's a strong base. All of its molecules are going to do that. To find POH, take the negative log of the concentration they've given us. And it comes out to 0.27. Now, guys, this is POH. We can't decide whether it's an acid or a base based on its POH alone. Our pH scale is what we use for that. Our next one wants the hydroxide concentration when they've given POH. So we're going to use our second formula here. Take 10 and raise it to the negative 4.1. So 10 caret negative 4.1. And we get 7.9 times 10 to the negative 5th. Molar. So what we should notice as the hydrogen ion goes up and we get more hydrogen ions in solution, hydroxide ion decreases. As H plus increases, hydroxide decreases. So in sample 5, guys, this is the last one. We're kind of putting it all together. This says, what is the pH? They gave us its concentration, and they gave us a substance. So our substance, whenever they give you one, you need to think, is this an acid or a base? And this one's a base because it puts out hydroxides. So when they give us this concentration, we have to ask ourselves, is this putting out H pluses or is it putting out OH minuses? And it's going to put out OH minus. So this concentration is our OH minus. So when I go and find the negative log of this concentration, I'm not going to be finding pH. What I'll ultimately be finding is POH. So negative log of 0.068 negative log 0.068. Let's say 1.17. But guys, again, that's POH. They want pH. How can I solve for pH when I've been given POH? We have another formula here. If you take a substance's POH and add it with its pH, it should add up to 14. So if we know substance's POH, we can find its pH just through subtraction. I'm going to have 14 and subtract the POH that we just calculated. 14 minus 1.17. And it comes out to 12.83 for the pH. And that pH makes a lot of sense because this is a base. It should be bigger than 7. So guys, we've solved for our pH, which is 12.83, and we've done it this way by first solving for POH and then subtracting. But there is an alternative strategy that I want to show you, another way of doing it, and it involves this equation right here. On your formula chart, by the way, both of these are there. So here is the first one, and then this one. Kw is 1.0 times 10 to the negative 14th, and we can get that value by multiplying our OH concentration and our hydroxide concentration together. So if I know something like the OH concentration, on this one, I went ahead and solved for POH, but what I could have done was use this equation, and since I know OH minus, I could have solved for H plus by dividing, taking Kw, which is 1.0 times 10 to the negative 14th, and dividing by my OH concentration of 0.068. This would be solving for H plus. So if I take 1, negative 14, that's Kw, and divide by 0.068, I get 1.47 times 10 to the negative 13. But this is not pH, it's just hydrogen ion concentration. Now, to continue and find pH, I could take the negative log of that. I'm just going to put the answer in so that it does it in the calculator. And it comes out to 12.83. So no matter what strategy you find is your favorite, either way works. So it's about picking which one works best for you. If you like this equation better, or if you like this one, either one works. Just make sure you're showing all of your work. Guys, in your notes that continues, I'm not sure exactly why I have to take credit for this mistake. I'm not sure why we ask you for molarity or why we ask you for acid or base twice. Sorry about that. But in this little chart, we have given you a piece, and then you're trying to find the other pieces. So first of all, pH is 7.8. Since it's a pH bigger than 7, basic. And then you can find the other pieces in any order you want. Since I know pH, I'm looking at my formulas. Since I know my pH, I could find my H plus by using this formula here. Since I know my pH, I could find my pOH by using this formula here. And then, depending on which one I've used already, I could find my concentration of hydroxide using either one of, these, one or there. It solves for concentration. It's really just a matter of preference. There's not a lot of space in these boxes to show your work, but down here we have several more that are really, really similar to the ones that we worked in our notes. And so make sure you're showing your work for these. I want to make sure and touch on number 6 because we haven't had anyone like this. So I made sure to do this in my first class period. Number 6 says, what is the pH of, so they want pH, and they gave us a concentration, and they told us what we're working with. Now, vinegar, you should know, is an acid. Okay, it's an acid we use a lot. You should also know that it's weak. It's not one of those 6 strong that we needed you to know. So notice they've told us something a little bit extra. It says assume 15% dissociation. It's not 100% dissociated. It's only 15%. That means not every vinegar molecule will break up into hydrogen ions and acetate ions. Only about 15% of its molecules do that. So this is its hydrogen ions, but that would assume 100% of those break apart. We need to find 15% of this. So we're going to take our concentration of 0.05 and multiply by 0.15, which is multiplying by our 15% there. 0.05 times 0.15. So truly, our concentration of hydrogens that are in solution is the 0.0075, considerably less than 0.05. Only 15% of its molecules break apart. Since it's weak, we're going to use this as its concentration of hydrogen and not this one. And then we just take the negative log like we would for any other pH calculation. And it comes out to 2.13. So the rest of them are just kind of asking you to think conceptually about pH down here, and I think also here. And then these are your math calculations. Guys, I'll do my best to have a key made for you and post it on Canvas so that you can check to make sure you're doing it correctly before we have a skills check next time.